our activities. And what I neglected to say to those of you who might be tuning in on tape is that I'm going to post the first part of test 3, and I will send an announcement when I do that. So be looking for that. Okay, so then where we are is we're talking about the prolific ability of carbon to connect to itself. One of the wonders of nature, the amazing ability of carbon to connect to itself in a variety of ways. And it, in many regards, leads to what I like to refer to as a closet rod. So carbon can connect to itself in a skeletal framework. Now, on the skeletal framework of carbon connections, you can now add other interesting elements. And typically, it is the chemistry of the other elements incorporated along with carbon on the framework that lead to all kinds of interesting chemistry. So interesting and so deep and profound that ultimately it leads to living systems. So again, what we kind of envision carbon as being is a closet rod that connects to itself so well that it makes a structure like a Christmas tree, if you like. And then on the Christmas tree, I hang various ornaments. And the ornaments are oxygen atoms, nitrogen, a smattering of sulfurs, and other things as well, many hydrogens. And the collection of all these atoms together are designed in a shape and designed with a connectivity and a desire for electrons and transfer of electrons so that it folds this huge structure into a very unique form. And then this form magically has activity that we say makes it animate or makes it alive. So we're certainly not going to be able to delve deeply into the understanding of what life is. I'm sure that's an eternal question humans have been pondering for a long time and will continue to ponder for a long time. But we are going to study the basis of this carbon connectivity and some of the practical applications that humans have designed with this carbon connectivity so that we can now make all kinds of interesting materials and things that make our lives so much more convenient, and things that we can do with these materials that are designed based on the carbon framework. So what I'm going to then do with regard to that is, of course, as I always do at a point like this, after some introductory period, we will turn to my slides. And on my slides, I have information relating to these carbon connectivities that we've been talking about. And where we are at this particular juncture is we are looking at the incredible connectivity that carbons connect to one another so that you get a nanoscopic structure turns into a visible structure. We can see a plastic because the number of carbons connected in it over and over again is so many that it becomes visible to the naked eye. And again, I've said this, that I've given this ballpark number many times over to you, but it's a pretty good reference point, I think. It would take about 10 to the 20 connected carbon atoms before you can see them. So there's an ridiculous, that the number 10 to the 20, ladies and gentlemen, is unfathomable. We can't even really understand how big 10 to the 20 is because we don't have a reference point to a number of that scale, really. But that is just an incredible number of carbon atoms connected together to even get the most minuscule visible strand of what we will call a polymer material. A polymer is a connection of monomers, and the monomers are really very simple units, and they concatenate together so well over and over again that they will make an incredibly huge unit. Now, we've already seen property like this when we formed a salt crystal. I can concatenate Na to Cl to Na to Cl over and over again, and I can make a chunk of salt. In theory, I can make as big of a chunk of salt as you can envision. Now, we know how big grains of salt are which come out of a salt shaker, and if I just continue to concatenate salt to itself over and over again, I can envision making a chunk of salt bigger and bigger and bigger. As a matter of fact, some of the hunters out there might recognize what we call a salt block, which is a big chunk of salt that a lot of hunters like to put in the field to entice deer, or they call it a deer lick or a salt block, whatever you might like to call it, to attract deers to a certain area where they might be hunted. Now, I think we can also envision, though, if I make a salt block bigger and bigger and bigger and bigger, the structural integrity of a chunk of salt becomes it's just not stiff, rigid enough to be very practically useful. I can't build a structure that I can live in out of blocks of salt. I can't build an automobile out of blocks of salt. Well, for many reasons. One, water solubility would be an issue. But even if we discount the fact that water might dissolve the salt, it's just simply not rigid structurally enough such that a huge, huge chunk of salt has structural integrity. It would actually get so heavy upon itself that it will break. But I know we're very aware that if I connect carbon atoms to one another over and over again, they can have incredible structural integrity. I can make very rigid structures out of enough connections of carbon atoms that I could easily sit on it. I can make plastic chairs, as we well know. I can design actually chunks of carbon designed correctly with the right connections placed in them can stop bullets. I can make a material known as Kevlar, which is a carbon-based material. So I can make incredibly sturdy, stiff, and strong polymers by connecting carbon atoms over and over again, certainly compared to the connection I can make for sodium chloride connected over and over again. Now, there's no doubt sodium chloride, sodiums and chlorines will connect to each other, and in theory should connect to each other as many times as you want. Yet the structure that they would make ultimately would have problems being applied to the many applications that we give to polymers in plastics based on carbon. And what it boils down to ultimately is the difference in the bonding that carbon takes when it connects to itself compared to the so-called bonding that sodium takes when it connects with chlorine. Remember, when I talked about the connectivity in sodium and chlorine to make sodium chloride, I called that an ionic bond. And an ionic bond is when literally electrons are transferred. The sodium gives up an electron, becomes positively charged. The chlorine gains an electron, becomes chloride, and becomes negatively charged. And now literally the electrostatics of the plus and the minus of the sodium and the chlorine stick them together and stick others together to it and stick this over and over again so that I get a concatenated solid structure. Well, opposed to that is what happens when carbon connects to carbon. As I've mentioned, because the way nature designs carbon atoms, they can't take electrons from neighboring carbon atoms. They have the same exact desire to gain or lose electrons as any other carbon atom. So the way in which they connect is completely different than transferring electrons from a cation to an anion. What carbon atoms do when they connect is share electrons between the carbon atoms. And ultimately, it is this sharing of electrons which gives the strength of the connection so that the properties of a bulk sample of plastic are dramatically different than the properties of a bulk sample of salt. one thing that you would find is it wouldn't dissolve in water because literally water molecules can rip the attractions between the sodium cations and the chloride anions apart and dissolve the salt in water. You pour the water on a polymer, a piece of plastic, it just rolls off of it because the water doesn't have the polarity to pull apart the connectivity between the carbon atoms in the plastic. Ultimately, what we can say is that the carbon-carbon electron sharing bond is way stronger than the sodium chloride electron transfer bond. So the shared electrons between atoms makes a particularly durable connection between the carbon atoms and allows the carbon materials built from them to have a much different properties than the properties of a connection of sodium chlorides when they transfer electrons. Okay, so what we're going to spend the majority of the day doing is running through a hierarchy of different ways of connecting a multitude of monomeric units of simple carbon structures to make a polymeric unit that we know as a plastic. We introduced the first of these on Wednesday of last week, and I'm going to fire my slides up now, and we're going to refer to the first of these that we introduced last time and talk a little bit about its characteristics that again, we've already done, but as I've said many times over, I don't mind being repetitive in the things that I say. I'm going to present my screen as I normally do, and then I'm going to click on the thing, and it's going to hit this, and then I'm going to hit this, and then as I always like to do, I like to tell you exactly what I'm doing. This now should have my slides up here showing, and we had already discussed this one, but let's again reiterate a little bit about it. I'm going to introduce what I call polyethylene. Ethylene is the old name that was given to ethene. We understand what the name ethene means. Ethene, since the name begins with F, 2 carbons, ene, double bond. So there's a share of 4 electrons between the 2 carbons. 2 from each carbon are chipped in. Now again, remember, since each carbon always, and no matter what it's doing, it always wants 4 connections. And since it essentially has 2 connections to a cousin carbon, each carbon then needs 2 additional connections. And in the hydrocarbon form of ethene, the 2 other connections that the carbon would have would be connected to hydrogens. So as you see on each monomer unit is an ethene. Each monomer unit has a double bond between the carbons, and each carbon, in addition, so that its nucleus is happy, has 2 other single bonds or sharing of 2 electrons between a carbon and a hydrogen. Okay, now what happens in the reaction? Chemists learned how to mix a bunch of this in a pot, take it to the proper temperature and pressure conditions, maybe stimulate it in some way. There's often a stimulation to get this to occur. Somehow we begin to rip apart the double bond. So it's essentially like this. There's 2 pairs of electrons between the carbons. Now all of a sudden, some process that chemists have devised takes this pairs and kind of pulls them apart so that they open up and grab their neighbor. So one of the lines from the carbon on the far left will grab the one to the next to the right, and the one from the next to the right will grab the further one over, and another one will grab the next one over. And when this is done, this will be the polymer form that comes from opening the double bond and connecting individual ethene units together. Now, what you should notice is that the chemical form hasn't changed. The connectivity has changed, and essentially what has changed is instead of all the carbons having double bonds, one of those double bonds has reached to its neighbor and grabbed it. There's the same number of carbons present as there is above. There's the same number of hydrogens present as there is above. There's just a different connectivity. Now again, the concatenation of this is so great that it becomes macroscopic. You can see this connection and it becomes known as polyethylene. And the name kind of says exactly what's going on. I'm taking the ethylene units or ethene units and connecting them from monomers into polymers. So you might also call this polyethene, but I think the trademark name, the name that it goes by industrially is polyethylene. And mainly that's because that's what the Brits called this. The Americanized name is ethene, the British name is ethylene. And this was pioneered or developed in the 1930s in England. Now, if I also showed this other slide, let me show the monomeric unit. One section of this would be, as you see here, why didn't I do this before? Let me turn off or hide the little button thing. Okay, so the monomer unit would be just this individual. This would be the ethene with its double bond open. That's the monomeric unit of this particular polymer. Now, I showed this slide already, so we just talk very quickly about it. Polyethylene was produced, as I said, in England, 1930s, and depends on the conditions in which you can react it. You can also branch this, and if you branch it or don't branch it, you get either high density HDPE or you get low density LDPE. When it's branched, you get LDPE. When it's not branched, I'm sorry, scratch that, reverse it. Oh, I'm sorry, that is right. I thought that was right. If you branch it, you get LDPE, and if you don't branch it, you get a HDPE. Meaning, if you stick limbs out on the sides of these chains, then the next chain above it won't be able to pack in as closely. So when they can't pack in as closely, then you get a lower density of the strands of the chains. When you get a lower density of the strands because of the branches, it changes the characteristic of the plastic. And what I show for the low density case is a picture to the left, which is a picture of a squeeze bottle. So we all have seen a squeeze bottle. We all get the idea of what the kind of plastic would be that would make this have that form. Now, we say on the bottom there that the first high density polyethylene product was made by Wham-O, and what Wham-O made with it was a Frisbee. I said Frisbee, but in actuality, they made a hula hoop with it. I think a little later, they made a Frisbee with it. Okay, so let's now go to another form of polymer. Now, before I'm going to do that, I'm going to back up here, and I want you to note that this would be the simplest polymer we could make from ethene, because it's pure ethene, C2H4 units that are used. Well, what happens if we functionalize the ethene? Now, what a chemist means when they functionalize is that they remove a hydrogen and hang a different material on there. As soon as chemists recognized what they could do with just the hydrocarbon form and how they can connect it, they started to mess with the ethene, substitute different chemicals in the place of the H's, and look to see what kinds of properties result from the type of connections that you get. So one of the first ones that was done was this one, known as polyvinyl chloride. Now, the monomer for polyvinyl chloride is known as vinyl chloride. And this, again, is not really the traditional name that we should actually use. The technical name for this is chloroethene. And what you see is that it is an ethene molecule that used to be C2H4. We popped off one of the H's on each of the units, and now it is C2H3Cl. So vinyl chloride The vinyl thing is the C2H3, and then you can hang anything on it to make something from that. So C2H3Cl is vinyl chloride, C2H3F would be vinyl fluoride, C2H3Br would be vinyl bromide. So chemists have this naming scheme for the C2H3 unit in addition to other naming schemes that are out there. So these individual units are known as vinyl chloride units. Now we're going to do the same thing that we did with polyethylene. I'm going to stimulate this in some way, details of which are probably easy to find out and easy to do, because believe me, this one is done over and over again. Probably this is, if not the most prolific form, very close to it. So you reach out, break the double bond between each monomer unit, they grab onto each other, and you form this. And this, as you can see, looks very similar to polyethylene, except now every other carbon has a Cl on it. Notice that is every other carbon has a Cl on it. Now I've drawn it so that the Cls are all above the carbon chain. I seriously doubt if that's the case. I would say they probably alternate. Why? Because of their size. The chlorines that are attached on there are pretty big. So probably more correctly, there'd be a Cl pointing up, then one pointing down, then one pointing up, then one pointing down. Probably. That's probably more correct. But what I would say is certainly something that is true is that even your mom and them have probably dealt with this particular polymer form, and they probably recognize it more correctly by its initials. And I think you can see the initials of this would be PVC. When you have PVC plastic, this is the kind of plastic you have. And if you're familiar with PVC plastic, you would recognize that we do a wide variety of things with PVC plastic. It has an incredible rigidity. It makes very nice, it has an incredible durability, meaning it doesn't decay or degrade very quickly, meaning if it gets wet or if it gets exposed by oxygen in the air, or probably equally importantly, if it gets exposed by sunlight, these things have very little effect on PVC. Now, contrast that to other materials, like for instance, paper. We take some paper and we leave it lay out in the sun for a while, and it gets rained on for a while, and the oxygen sits out in the air for a while. I think we all know what happens to the quality of paper after a lengthy period of time. Now, I would like to point out to you, paper is a polymer as well. We'll say more about its polymeric form. Maybe if not today, we will do so on Wednesday. So it is a polymer too. It's just a naturally occurring polymer, one made by nature as opposed to one made by man. Okay, so returning to my original statement here, the characteristics of materials like PVC are their durability. The three major agents of degradation on this planet, I already mentioned them, but let's repeat them because it is very important. They are air, and in particular, oxygen in the air. Oxygen in the air destroys lots of stuff. They are sunlight, and of course, that's high energy radiation coming down on this planet constantly. And of course, there is water. Water is relentless and incessant and has a lot of properties of polarity internally itself that helps to degrade materials. Things like metals, iron, even aluminum cans, a lot of these materials very susceptible to long-term exposure of water, sunlight, and oxygen from the air. But materials like plastics seem to be very resistant to degradation from attack by water, sunlight, or oxygen from the air. Now, I would say that, of course, this is one of the incredibly important aspects that makes these polymers so useful in everyday applications. But there are other things as well. You should be able to think of other things besides the durability. And another thing that makes these incredibly useful is their density, the weight of them compared to how much space they take up. These are very light materials. So rather than, if you make some, you could make similar materials from metals, but when you make them from the metals, they're going to be much heavier objects. Another thing, they might also be affected by magnets and things of that sort. And also, there's also the fact that the iron in them is subject to attack from oxygen in the air that degrades iron into rust, which is also a big problem. So once we design materials such as this, then the applications to making products from them made them sort of take over as the go-to materials to use to make such a wide variety of objects that I really don't even need to go into, because I know we're all familiar with them. Now, before I move on, I do want to say one more thing. One of the detriments of plastics is also their durability, meaning they don't degrade by the normal pathways that things on this planet are generally degraded by. And those are the attack of water, sunlight, and air. Because they're so durable to those three agents of destruction on this planet, they don't go away. So if we're done using the plastic, then the plastic doesn't degrade. Well, you say, well, that's okay, I'll just throw it into the garbage. Well, that's a problem. Because when you throw it into the garbage, we take it to the landfill is full of plastic. And the plastic is not going anywhere for quite some time. And I think, as we're all aware, it has also now somehow managed to make its way into the oceans. There are literally floating islands of plastic in the oceans that are really kind of bothersome. So there are certainly issues that come about. We get the benefits of the durability of the plastic that we're making, but we also suffer the consequences of the durability of the plastics that we're making. It's kind of an irony that we can't avoid. Okay, now before we move on to the next one, though, I want to say some more things about this. Is the polymeric unit, as you can see, would be a C2H3Cl. That's one unit. There are just a bunch of them connected over and over again. And then you can make all kinds of properties, such as, of course, all those white pipes that you can buy. You can buy pretty much all the pipes that we make and put in our houses now, not all, but the majority of pipes that we use in our houses are now made from PVC. Chairs are made from PVC. Just a whole variety of things are made from PVC. Now, PVC itself is kind of rigid and kind of stiff, but if you treat it with modifying materials and you dissolve them into the PVC, you can change the characteristics of the PVC. So what scientists have done, material scientists have spent a great deal of time doing this, is mixing things in with the PVC. And one of the familiar things that they mix in are things that are known as plasticizers. Now, exactly what is a plasticizer in particular? Well, there's a wide variety of these as well. And a lot of the industry trade secrets don't want to let you know exactly what they use as a plasticizer. But all we need to think of it is something I can mix with the polymer to change its native characteristics into having different characteristics. And when they put plasticizers into PVC, it changes it into what we call vinyl. So if you get, say, a garden hose is also made out of PVC, just like a water pipe or a lawn chair. might be made out of PVC. Of course, though, the characteristics of the garden hose are quite different than the characteristics of the lawn chair or the water pipe. So it's the addition of the plasticizer to the PVC that changes its characteristics. What the industry calls it when you mix the plasticizer with the PVC, they call it vinyl. And I'm sure we've all heard the name. If you have something made out of vinyl, it is just PVC, but it's PVC mixed with a component that makes it a little softer so that it's a little more flexible. You can make vinyl jackets. You can make vinyl little containers with zippers on them so that you can store items in them. You can make vinyl seats in a car. You can make vinyl coverings on the dashboard. So back when I was a kid, all the cars had vinyl roofs. Don't ask me why. It was just a big trend. Everybody wanted a vinyl roof on their car. There was still steel, but then they covered the steel with vinyl, made vinyl roof cars. Just a popular thing to do at that time. Now, though, what happens is over a large period of time, the plasticizer will deteriorate, maybe kind of evaporate out of the vinyl, otherwise degrade from the vinyl. And when that happens, the vinyl will stiffen and crack. So if you've seen old car seats, new car seats that are covered in vinyl are nice and pliable and soft, and you can sit in them. Then after a couple decades, what happens is the vinyl in the seats begins to lose its plasticizer. After it loses its plasticizer, the vinyl will develop cracks. And I'm sure that somewhere along the line, you've seen some old vinyl that is kind of stiff and rigid and has lost its pliability and will be cracked because of the fact that it's lost a bunch of plasticizer. Now, if you get certain materials and put them on your vinyl, it will keep it, it kind of replenishes the plasticizer that is in the material. Now, what do they call that stuff that you put on your car and wipe it on your car? I think they call it Armor All. Those of you that are into your cars might know that you can make your dashboards and your certain components of the plastic in your car. You can make them look new. You can make them just seem more pliable and soft by putting Armor All on them. The Armor All in some way sort of rehydrates, if you like, the vinyl, puts the components back in like plasticizers, and it kind of makes the vinyl seem like it was when it was brand new by the placement of the so-called Armor All onto the vinyl. So that's really what's going on when you put that stuff on there. Certainly you're cleaning it, yes, as cleaning agents as well, but it also has these softening agents so that it kind of regenerates the plastic itself. So other derivative forms of vinyl lead to all kinds of things. Believe it or not, you can make clothing out of it, and the clothing material that was made from putting certain plasticizers into PVC was a material known as Orlon. It's not nearly as popular as it was in the 1950s and 1960s. But believe it or not, bubble gum is also plasticized PVC. How do you think you can get those nice big bubbles to blow with bubble gum? Now, I'm not talking about chewing gum. I'm talking about bubble gum. Okay, so chewing gum is actually a different form, polymeric form, than is bubble gum. Bubble gum, in order to get those nice big bubbles like that, has PVC with a certain plasticizer in it, and of course color and sugar and other things as well. And we all know the characteristics that we can get from bubble gum. Okay, now let's go to another functionalized form of ethene. So if I took plain ethene, I could make polyethylene. If I took ethene with one chlorine hooked to each monomeric unit, I could make PVC. Now, if I hook 2 chlorines to each ethene unit, so these will be the basis of this next polymer. So the characteristics of this material will be different than the characteristics of either a PVC or polyethylene. Notice how I've connected the 2 chlorines. Now, I also want you to notice that there's a variety of ways that I could put the 2 chlorines onto the ethene. There's actually 3 different ways of doing this. I can put the 2 chlorines both on the same carbon. That's what I've done in these units. Notice both chlorines are hooked to the same carbon. That the name that is given to this kind of says it all. It is 1,1-dichloroethene. And the 1,1 means that the chlorines are hooked to the same carbon. And the dichloro means 2 chlorines hooked to the carbon number 1 in ethene. The ene says there's 2 double bonds. The F says there's 2 carbons. So chemists have devised this hierarchy of naming that we talked about before that very explicitly tells you the connectivity of the atoms and exactly what atoms are in this particular unit, these particular units. So this is 1,1-dichloroethene. I want you to also notice I could have 1,2-dichloroethene. 1,2-dichloroethene would have 1 chlorine on one carbon, 1 chlorine on the other. But I would also like to point out to you that there's 2 ways to do that as well. If I made 1,2-dichloroethene, I could put both chlorines on the 2 carbons above, or I could put 1 chlorine above the C's and 1 below. So they have names for those as well. If it is trans 1,2-dichloroethene, then the chlorines are across from one another, 1 above and 1 below the C's. If it is cis 1,2-dichloroethene, then the 2 chlorines are on the same side of the carbons. So believe me, it gets really detailed when you start to name complex organic molecules based on the name telling you where to stick everything at. Okay, so this particular polymer I'm talking about has both chlorines hooked to the same carbon. We're going to do the same thing that we did before. I'm going to invoke a chemical reaction, and when the reaction occurs, the carbons are going to reach out and grab each other, and they're going to connect together like this. They're again going to make a polymer. It's a little different than polyethylene, which would have all H's. It's a little different than vinyl chloride, which would have every other carbon having 1 Cl. Now, every other carbon, as you can see, has 2 Cls. This, when you make it into sheets, it actually makes very nice, transparent, thin sheets. And when you do so, the trade name of polydichloroethylene is Saran. So that's the trade name, meaning this is what DuPont picked as the copyrighted name that this is called when you use it in processes. And when you make things out of Saran, Saran wrap is thin, transparent sheets of this that I'm sure your mom and them probably have in your kitchen right now. So Saran wrap is made from Saran. Saran is polydichloroethylene, and it doesn't have to come in the sheets that you see it in, but it's particularly useful when you spread it out into these thin sheets because it's transparent. You can see through it and put it over the top of a bowl, and it stretches really nice, and it actually grips really nice. So we've all seen the characteristics of this, and we all get the practical utility of this as well. Okay, so let's now look at the next form of ethene-based polymers that I want to discuss. This one will be polypropylene. Now, remember what the name prop means. Prop means a 3-carbon connection. That's what prop means. Okay, now let's contrast this to polyethylene. That meant a 2-carbon chain. So in propylene, it is a 3-carbon chain. So what I've done in these pictures is shown that carbon chain of 3, but kind of made it look like a branch. So you see I have the double bonded carbons, then one of the carbons has a branch, but the branch is a methyl, as we named it. It is a CH3. That is a methyl group. Remember, methane is CH4. Methyl group means pop an H off and attach. So I would attach the CH3 to the 2 doubly bonded carbons. Okay, now notice these individual units are called propene. Propene means 3-carbon chain. One of the bonds is a double bond. So this is propene. Now, again, I can open the double bonds on propene. Let the double bonds grab each other, neighbor to neighbor to neighbor. And now I will get a branched hydrocarbon that every other carbon has a methyl group. And this, if you put a hydrogen in those locations, it would be polyethylene. If you put a methyl in these positions, instead, you now have polypropylene. Now, the difference between the plastic made from polyethylene and polypropylene is that polypropylene is stiffer and more rigid and turns out to be more durable. And we make different things from them, as we will discuss on the next slide. The orientation of the methyl group of the polyethylene gives different kind of characteristics to the stuff that you make from it. And this is one of the most prolifically produced plastics, polypropylene. You can see from this statement, we make about 5 tons of it. I'm sorry, 5 million tons of it every year. Some of the things that we make out of it are carpets. So it's used to make carpets, things that we hang in automobiles, bottle caps, hiking clothing. What's a prosthetic? Well, that's like a fake limb. So polypropylene is used to make fake legs and fake arms and things of that sort. But it's also, as you see, the durable clothing I'm talking about is, I don't know, stuff that would be clothing that you might wear when you're cleaning, industrial cleaning and stuff like that, so that it's resistant to tearing and things of that sort. So stuff that you would wear that feels plasticky, that also protects you from tearing and things penetrating it. That'd be made out of polypropylene. We've all seen little bottle caps. That's not what they use to make the plastic bottles. I'll show you that probably upcoming here very shortly, but it is used to make the caps. And probably the most common use of it is fibers that we can spin into strands. You can make carpet out of it and all sorts of stuff like that. Okay, now let's continue this theme. Let's now take tetrafluoroethane. Oh, I'm sorry, that's a bad name. I said 1122 tetrafluoro. That should not be tetrafluoroethane. That should be tetrafluoroethene, because if it was ethane, that would be a single bond between the C's that you see there. So that's my bad. This is made from 1122 tetrafluoroethene. So I apologize for my typo there. That should be an E instead of an A in that word. But this is also a very familiar polymer to us. Now notice it's just ethene. If these were all H's instead of F's, it would have the characteristic of polyethylene. If you put a Cl on there instead of all these F's, it would be like PVC. But now I'm going to put F's on instead of H's. And the properties that arise when you put F's on instead of H's are very interesting. First of all, we make what we'll call polytetrafluoroethylene, But this has a trade name that I'm sure you've all heard. When you make C2H4 into polymer, you make what we know as Teflon. Now, Teflon, of course, makes these coatings that you put in pans and things of that sort, but Teflon has many other usages than this most familiar one that I'm sure your mom and them have talked about, having a Teflon pan that they use. Teflon is also very familiarly used in plastic pieces that we want to be able to rotate and move when they're lined up by each other. So it kind of makes things that can be turned and twisted without breaking them down. So we use it to make little valves. So if you have like a little valve that you can turn and open, it's made out of plastic. The plastic that they make the valve out of is very typically Teflon, because Teflon is kind of like a slippery plastic. When you put two Teflon surfaces next to each other, they can slide across each other very easily. That's the whole point of you coating this pan with the Teflon. It's so that things won't stick to it. They slide off of it very easily. Now, one of the problems, though, is if you put a metal utensil in your Teflon pan, the metal utensil can scratch the Teflon off. And we're all familiar with that. If you scratch your Teflon pan, you cut down to the metal in the Teflon pan. The worst part about that is, guess where that Teflon you scratched off went? It didn't evaporate. It went into your scrambled eggs. So you have to be real careful with a Teflon pan if you're using the wrong kind of utensils that can scrape the Teflon loose, because then you begin to ingest Teflon. And I certainly wouldn't advise investing or ingesting too much Teflon. Okay, now there's a few more other polymers I would like you to be aware of. This one is the connection of poly, as you can see, not poly, it begins with phenylethyline, or this is a material known as styrene. Now notice what a styrene molecule is. It's an ethene where you take off an H and you attach a 6-member alternating single and double bond carbon ring. Now the alternating 6-member double and single bond carbon ring is known as benzene. So this is a benzene ring attached to an ethene unit. So each monomer has a benzene ring, and coming off the benzene ring is an ethene unit. Now, in the conditions of the reaction, the double bonds in the rings are stable and don't break. It's really hard to disrupt those C-C double bond connections in the ring system. It is not, however, difficult to disrupt the C-C double bond in the ethene chunk sticking off the ring. So when you make the conditions of this reaction go, you open up that double bond on the carbons, and then they grab onto each other, and you make this connection. Now, once again, I've drawn it with all the rings above the carbon chain, and I've kind of put the other H2 thing between it, connected all together. I didn't put the C with HH, C with HH, C with HH, but every other carbon has 2 hydrogens attached to it. Every other carbon has 1 hydrogen and 1 benzene ring attached to it. Now, once again, like I said before, I am drawing this with all the benzene rings on the same side of the carbon chain. That's virtually not going to happen. That's kind of impossible to happen. There will be one above, one below, one above, one below, but I was too lazy when I was drawing it to do that. I was just cutting and pasting and just sticking it all back together like I did. So this is the way I drew it. So every other carbon has a benzene ring on it, And chemists have known the original compound that this is started from as styrene. So when you polymerize styrene, you get polystyrene. Now, what material chemists have learned is now you can do all kinds of interesting things with polystyrene. In particular, when you inject gas in it. So when you do this reaction, it makes a big pot of liquid. And the liquid is at high temperature. So you do it at a temperature where this is in a liquid form. Now you bubble gas into the liquid and you begin to cool the liquid. So you're bubbling gas through liquid polystyrene, and as it cools, it solidifies. And when it solidifies, it makes what we call styrofoam. So styrofoam begins out as liquid polystyrene. They bubble gas through the polystyrene, and the gas bubbled through the polystyrene makes little pockets of air in the polymer. And the little pockets of air in the polymer give it the characteristics of styrofoam. And again, your mom and them have seen styrofoam. It's kind of a very light, low density. Why is styrofoam so light and low density? Because it has so much air among the polymer strands. There's a whole bunch of air in there. It's compressible. You can make these packing peanuts out of it. And we all know you can take the packing peanut and you can squeeze it and it has some bounce to it. So the styrofoam packing peanut is this very light, it almost floats in the air, form of plastic that has this cushiony resistance to compression. So of course it has that application. And in addition, because there's so much air in the styrofoam, it turns out to be a great insulator. Now, what does it mean to be a great insulator? You're not affected by hot or cold. You don't transmit heat through you very effectively. So you keep cold things cold, or you keep hot things hot, because you don't let heat to flow in or out of the walls of the styrofoam. Now, of course, it does, but it doesn't flow in and out as readily as it would if you had, say, a metal container or other forms of plastics as the container. The styrofoam container, and again, I will mention, it's mainly because of the air in the structure of the polymer. The air itself is the good insulator, and this is something we will discuss in more detail in our next unit of discussion. But the air is the good insulator. Since there's so much air in the polymer itself has a pretty good ability to not be affected by changes in temperature. So the temperature of anything contained in the styrofoam cup is regulated. Not forever, but at least temporarily, the styrofoam has the ability to keep temperature from changing the effects. Now, if you don't put air into the polystyrene, it will make very rigid plastic. Rigid like the stuff that you make phones out of. Okay, so the stuff that you make, I'm talking about old dial phones, the kind of rigid plastic they're made out of. The kind of stuff that your computer casing is made out of. That's made out of styrene, polystyrene. So when you put the air in, the characteristics of it are quite different than when you don't put the air in it. Okay, so what I want to mention so far is all the polymers we've discussed were based on ethene. If you use plain ethene, you make polyethylene. If you use propylene, which has a ethene with a methyl on it, you make polypropylene. If you use ethene with fluorines on it, you make Teflon. If you use ethene with benzene on it, you make styrene. If you use ethene with chlorines on it, you can make PVC. You can make saran wrap. Now, of course, chemists have figured out how to make polymers out of other materials as well. So let's just look at some other kinds of polymers and the kind of reactions that they use to do them. Instead of doing this so-called addition reaction where they open double bonds, so far all the polymers we've seen have ethenes that grab across each other and make connections that way. They do these things where they do condensation polymers. And in a condensation polymer, you take water and remove water out of the two connecting units, stick them together, and they polymerize. So in a condensation polymer, water is shed as the individual units connect. And I will just offer a couple examples of those. If you connect this stuff, which is ethadiol, which is an alcohol with two OHs on it. Okay, so this is a ethene chain that has alcohol groups. Alcohol groups are OHs. And you connect it to this other stuff, which again, I wouldn't expect you to know what this is, but it's known as terephthalic acid. It's got a benzene ring and two other connections on its outside. And you let these grab each other and get rid of water, they connect in this fashion. And the reason I'm showing this is that this is another very commonly used, very important form of plastic known as PETE or PET or polyethylene terephthalate. Now, this is called a polyester because these reactions that we're doing are known as ester reactions. So when you have polyester, you're doing connections of molecules of this type. Now this polyester, and I'll show you some examples of the stuff that we make from them, forms the very familiar kind of plastic that we use in disposable water bottles or a little Coke that we buy off the shelf at the 7-Eleven. So those are made of the plastic that is formed by mixing polymers together of these type that are known as condensation polymers. Now, the other thing I want to point out that's going on here is that these polymers are made from different monomeric units. Previously, when I made polyethylene, polyvinyl chloride, Teflon, polystyrene, or any of the other ones we've shown before, I used the exact same monomeric unit. I would hook two ethenes together to make a unit of polyethylene. I'd hook two vinyl chlorides together to make a connection in PVC. The monomers were exactly the same. In this case, the monomers are different molecules. So we call that a copolymer. So a homopolymer has all the monomeric units exactly the same. And most of the examples we have talked about are homopolymers. Polyethylene, polyvinyl chloride, polypropylene, polydichloroethane, polyvinyl chloride, I said already, Teflon, all those were homopolymers. If you use copolymers, they have different monomeric forms. And the PETE, PET, is a copolymer because it has different units. As a matter of fact, anytime you have a condensation polymer, condensation polymers are all going to be these so-called copolymers. Now, just one more copolymer that I'm going to show. This again will take a molecule that starts out with OH on both ends of it, just like we did in the PET connections. But now instead of the thing with the benzene ring, I'm going to take something that has actually some nitrogens in it. And when I connect these two together, again, I'm going to shed some water molecules. So this is a condensation polymer. It's also a copolymer because I'm taking these two different monomeric units. When I connect these together, I make nylon. And nylon was one of the miracle materials of the 1930s and 40s. This really changed everything when we began to make nylon, because it turns out nylon can be stretched into threads, and then you can weave the threads together and you can start to make all sorts of stuff out of nylon, all kinds of stuff. Everything from pantyhose to parachutes to all kinds of clothing items can be woven from nylon. So this really found itself in a wide variety of usages in a variety of industries that people found they could make products out of this. I might say a few of them here. It's actually called a polyamide, not a polyester, but that's neither here nor there. I'm trying to pop these things up here because they're out of order. I'm sorry about that. First thing they made out of it, as it says there, was pantyhose, and they were going to call it, as it says there, no run, because of the pantyhose that they made out of it, but they changed the name to nylon, and we could make all kinds of materials out of it. So, like I said, they used it to make parachutes in the Army and all sorts of other things. Turned out to be very important for manufacturing all kinds of clothing items. Okay, that's going to be our tour of the polymers. Now what I want to do is say a little bit about the prolific nature of carbon in other areas of equal or even greater importance, and that is the chemistry of life. And the chemistry of life, just like the chemistry of all these manufacturing things we've talked about, involves carbon-based chemistry. So we're not going to delve deeply into the ideas of carbon chemistry, but I certainly want to point out to you some of the very important applications of carbon in nature. Now, first of all, we should recognize nature was the original polymer former. Way before humans learned how to synthesize polymers, nature itself was synthesizing polymers. One of the earliest examples of polymers that humans took advantage of was rubber. They could harvest this sap from certain types of trees that were found in tropical regions, and they could use they could process this sap in various ways and form it into the material that we know as rubber. Now, the original name rubber actually came about because they found that this stuff was great for erasing lead pencil marks. So the first application of rubber was the fact that when you wrote with a lead pencil, you could take a chunk of this rubber, rub the lead pencil onto the rubber, and it would remove the lead pencil from the place that you marked it on the paper. Not making that up. That's where the name rubber came from. But very quickly what they found was, again, by changing the characteristics of the rubber, in particular a scientist by the name of Goodyear, should be a familiar name, found how to link the rubber together. Rubber in general, just like the form of the pencil eraser, is kind of pliable and soft and doesn't have really good rigidity. Well, this individual by the name of Goodyear, again, a name that should be familiar to you, learned how to cross-link the polymer change and make it more rigid. Then when they learned how to do that very quickly, they learned how to make things that were durable, yet they were very pliable, that could hold air, they were resistant to allowing air to pass through the walls, and they could make tires out of this modified rubber that they had taken from the sap of these trees. So the original rubber industry that was very important certainly came to pass in the mid 20th century, 1910, 1920, 1930, when the growth of the automobile industry went nuts. And instead of having rigid metal or wooden tires that had a jolting the reason they liked the rubber tires was if you put air in them, that created a huge cushion. So when you're riding on the rubber tire, it's not so much, it's also, of course, the traction. You get good traction or grab to the surface underneath the tire. That's one good aspect. But a more important aspect is that there's a cushion of air in the rubber tire. So as you're jostling along on the surface, there's a great deal of shock absorbing characteristic due to the rubber tires. If you had wooden wagon wheels like they had in the old days, and you rode around down some nasty rutty roads with those wooden wagon wheels, you would quickly learn how jolting and jarring the ride would be as a result of the lack of cushioning you get from the rigid structure of the wooden wheels. So the main benefit of these rubberized tires was the shock absorbing ability they provided to the ride that the device you were trying to go in was provided with the presence of that air cushion. So this is when a big issue occurred in the 1920s, 1930s, 1940s. As the world went to war and the Germans wished to mobilize their forces, they needed tires. And at the time, the tires were all based on natural occurring rubber that had to be harvested in tropical areas. They couldn't grow the rubber trees in Germany. They had to import the rubber from either South America or regions of Africa. And the Allies blockaded, put battleships, warships, or whatever in the regions where the Germans could acquire the rubber they needed to make tires, but not only tires, also hoses and things that went into their engines. So if they wanted to mechanize their army, they needed a certain amount of rubber in order to pull this off. Rubber at the time was natural, not synthetic. So this became a real issue for the German army. So the German scientists made a material now known as neoprene. Neoprene is synthetic rubber. So they learned how to synthesize their own material that had similar characteristics to what naturally occurring rubber had, which nature could make. And they could then use the neoprene to make hoses, things that it's still used to make hoses. If you get a radiator hose in a car, it's got this certain kind of rubbery feel to it, but it's not quite the normal rubber that you might find in a car tire. Well, those kind of hoses are made of this synthetic rubber, which we now know as being called neoprene. Okay, so in any event, my diatribe there began because nature itself makes rubber. And we have learned to mimic some of the reactions in nature in order to make our own artificial polymers that can take the place of things like rubber. Now, rubber is not the only polymer made in nature, and we'll talk a little bit about that on some of these upcoming slides. So what we are now moving into is the study of so-called biochemistry, which is the study of the chemistry of molecules that sustain and are important to sustaining life. So there's a wide variety of molecules interested in biochemistry. We're going to mention a few of these, not all of them, but there are carbohydrates and vitamins and nucleic acids and lipids and just all sorts of things that we could discuss with regard to this. So let's just begin a discussion of biochemistry with probably a name of an important biochemical molecule that we do have some familiarity with. Your mom and them probably have some familiarity with, and that would be what we know as a carbohydrate. Now, the name carbohydrate is kind of a misnomer. We really didn't know exactly what they were made of when we started investigating them, and when we gave them this name. The name implies carbohydrate, carbohydrate. Of course, the carbo part implies carbon. The hydrate part implies water. And to this day, anything that is a carbohydrate has the general formula CnH2ON. So a carbohydrate can be made from 6 carbons and 6 water units. A carbohydrate can be made from 12 carbons and 12 water units, and so forth. But the connectivity of the carbohydrate isn't CH2O, CH2O, CH2O. The CH and O are spread throughout the molecule, but they all have the general form as if they are individual units of the same number of carbons connected to the same number of waters. Now, so that's the nature of that name. So a simple carbohydrate is glucose, and it turns out that this is probably the most important of all carbohydrates. So let's say a few things about glucose and where glucose is of, and why glucose is of such importance. We might as well just simply say it here. Glucose is the key to life, at least animate life of greatest importance to us. Now, there are forms of life that exist that don't rely on glucose, but the two most important forms of life rely entirely on glucose. And the two most important forms of life are either plant life or animal life. And all plant life and all animal life is based on glucose. In plants, it is produced, so glucose is made in plants in processes known as photosynthesis. Glucose is consumed in animals in their metabolic or energy producing processes. So there are two very important reactions that we need to focus on with regard to both photosynthesis and respiration. You know what? I don't really have enough time to give these justice. I think I'm going to stop there because I don't want to start the discussion of photosynthesis, respiration until I want to give it its due. So we'll start it on Wednesday. I am going to post some things, so I'll be putting out an email that will have an assignment for test 3 that you need to be looking at. So look for my announcement so when you can start working on that. So until next time, peace out. Ah.